Hello, everyone, and welcome to today's webinar. My name is Patrick Hawkins. I'm a design engineer in the Thorlabs Advanced Photonics department, and I'll be moderating today's talk. Today's presentation is Using Single Mode Fiber and will be given by Dave Gardner. David has been with Thorlabs for over 10 years and is currently working as a senior process engineer. Within this role, Dave leads the development and production of our fluoride fiber, while also supporting the characterization, testing, and R&D for our silica and fluoride manufacturing teams. Dave also plays a major role in the development of new fiber products and processes. This webinar is part 2 of a 2-part webinar series on single-mode fiber. In this section, we're going to continue to demystify single-mode fiber with some theory and practical guides on using single-mode fiber. The previous section, Understanding Single-Mode Fiber, is available at thorlabs.com in the recorded webinars section for anyone who missed it or anyone who'd like to review. I've worked in the product development team at Thorlabs for nearly 10 years, during which time I've worked with Dave quite a bit on R&D projects, new metrology equipment and processes, and introducing new fibers and accessories manufactured in our Advanced Photonics division. We are accepting questions throughout the entire event. To submit questions, just click the Q&A button in the top right of the screen, and Dave will address those at the end of the talk. Okay, I'll turn it over to Dave now for part 2 of single-mode optical fiber.
Thanks, Pat, and thanks to everyone who's joined us for today's webinar. I hope you enjoy it. Diving right in, here's a summary of what we're going to be going over today. As Pat said, this is part 2 of our single mode webinar series. So in part 1, we talked a lot about how the light travels through the fiber waveguide. And today, what we're going to go over is how do we get light into the fiber? How do we get light out of the fiber? And by extension, working with the fiber in the real world in a lab, how do these concepts from part 1 translate into actually using single mode fiber in an application? Just like part 1 and my other webinars, the idea here today is a high-level overview, really focusing on conceptually understanding what's going on with single mode fiber, rather than focusing on, for instance, equations. That being said, you are going to see more equations in the slides today compared to past webinars. I'm not going to necessarily go through all the math, but this talk will be available on YouTube afterwards. So if you want to go back and write down the equations or things like that, don't feel like you need to during the actual webinar. Yeah, and like I said, the idea here is a practical guide for working with single mode fiber, especially in something like a laser lab environment or general use, rather than focusing on pure telecom applications like a lot of single mode material out there talks about. So yeah, like I said, we'll have a short review on what we went over in part 1, how the light travels through the fiber. Then the first major section is how does the light exit the fiber, output of single mode fibers. Then we'll talk about fiber coupling. And then finally, we'll finish up with a short section on directly connecting 2 fibers together. So yeah, little review. As we said in the last talk, single mode fibers, they only transmit that one fundamental mode, LP01, in the fiber core between the cutoff wavelength and the bend edge. And if we were to cross-section a single mode fiber and look at it on end, like we see here, and we actually looked at where the light travels through the fiber, we'd see something like this, where we have this certain intensity profile of the light, and that extends to a region a bit bigger than the fiber core, which is what we see here. Actually, it extends larger than the core to the extent that about 45% of that optical power travels through the cladding. And if we want to talk about the index profile here, this spatial index profile or intensity profile, that can be precisely described with a Bessel function, which gets complicated pretty quickly. Luckily for us, it's very close to the intensity profile of a Gaussian beam. And by very close, you can see a comparison here in this graph. So close, in fact, that for almost all applications, we can really treat this intensity profile that travels down the fiber as Gaussian. And you'll see that that really simplifies things in a lot of the material we're going to cover today. It's also worth noting that this Gaussian beam or Bessel beam traveling through the core of the fiber, it's very different than that light pipe model we've seen for multimode fibers where you have a ray of light and it bounces off the interface on one side, then the other side, and undergoes total internal reflection. This beam of light traveling down the single mode fiber, to think of a ray optics interpretation of it, it's really like that beam is traveling down the length of the fiber, and it kind of sees both sides of the interface at once. So it's touching the interface all the way around simultaneously as it moves through this fiber waveguide. So if we want to put some numbers on the region where the light travels in the fiber, a very useful parameter is the mode field diameter. This is a measure of the diameter in which the intensity falls to 1/e² of the peak in the center of the core. And this region is going to be larger than the core diameter, typically a few microns larger. And this would be analogous to the beam radius or the beam waist of a free space Gaussian beam. That'll come up a lot in this talk. The big difference is because this beam is in a waveguide, it's in the fiber, it's a constant diameter along the length of the fiber. So that mode field diameter stays constant as we travel through this fiber waveguide. And we can calculate the mode field diameter using these equations here. So it ends up being a function of the fiber core diameter, the fiber's numerical aperture, and that means the index contrast between the core and the cladding, and the wavelength of light. Okay, with that short review out of the way, now we're going to transition into talking about how does the light exit the single mode fiber. So how does this light that's coupled into this waveguide go from that to free space? Now, at first glance, we see a diverging beam coming out of the single mode fiber, not unlike that of a multimode fiber. And in this talk, we're going to do a lot of comparing this multimode light pipe ray optics concept with the behavior of single mode fibers. So yeah, at first glance, like you can see on these microscope images, we have a flat cleaved fiber, and then we have a beam of light exiting. And the multimode fiber, we have many rays that can bounce around in the core and then exit at up to a certain angle of incidence. So some sort of solid angle is filled by the output of the fiber. The single mode fiber at first glance looks very similar. But what we're going to see in a minute is that the mechanisms at work that make this beam expand are actually very different for the single mode fiber. That's what I'm kind of getting at in this slide. So yeah, for multimode fibers, you can use this ray optics model where we have a certain acceptance angle or a certain output angle, and that has to do with the angle of incidence on the core clad interface to get total internal reflection. And we can talk about the NA as the comparing the core and clad index, but also a measure of that angle of light that's output from the fiber. For single mode fibers, we can't use this model. Instead, we're going to have to look at the way Gaussian beams behave, and that's how we're going to model the output of a single mode fiber. So yeah, the next couple slides are just a review on how Gaussian beams work in free space, and then we're going to apply that to how they work in the exiting fibers. So Gaussian beam, speaking generally, is really any kind of beam with a Gaussian intensity profile, or a intensity profile that can be described by this equation here. What that intensity profile looks like is what we see here. And we would see this intensity profile at any point along the beam. You're going to get the same shape of that intensity profile. However, the diameter of the beam is going to evolve along the length, so it never stays exactly constant. It's either going to be getting smaller or getting larger along the length of the beam. We call the beam radius would just be the 1/e² diameter or radius of the beam at any point. And at the minimum, where the beam is the smallest, we'd call that the beam waist. So that's the 1/e² radius at the smallest point along the length of the beam. So as you can see here with these cartoons, the beams are always going to have a beam waist where they're the smallest, and then they're going to get larger on either side. We can have beams with different size beam waist, and that's going to directly affect how quickly they diverge on either side of the beam waist. So speaking generally, if we have a smaller beam waist, that it gives us a more divergent beam. Additionally, wavelength comes into play here. So shorter wavelengths, all else held equal, also mean a more divergent beam, even at the same beam waist. So examples here of a large waist, low divergence, small waist, high divergence. Now to put some numbers behind these concepts, we can use some equations here to model a Gaussian beam. So again, the 1 over e squared beam radius, omega, is used in calculations. An important parameter is called the Rayleigh length. So that is the distance from the beam waist, that's the smallest diameter, where that diameter grows by a factor of square root of 2, or the cross-sectional area doubles. That can be very short for highly divergent beams, like what this cartoon shows, and it can be very large for beams that are well collimated. In this Rayleigh range, the beam doesn't diverge linearly with distance from the beam waist, but if we get out into the far field, we actually do see linear divergence. So we can calculate that divergence angle with this equation, and then with these equations, we can calculate the Rayleigh length and the beam radius. Notice this is only a function of the beam waist and the wavelength. Again, those are the two things that determine how quickly this beam is gonna diverge. So that's a little summary of Gaussian beams, and now what we're going to talk about is what does that have to do with single mode fibers? So here's the model of how light exits a single mode fiber. As we said, when we travel along the fiber core, we have a beam that's roughly Gaussian, and it propagates at a constant diameter because it's coupled into this core, this waveguide. However, as soon as we get to this end facet, where we're going to transition from fiber to free space, now we have a free space, basically a Gaussian beam. So this beam starts to expand right as we leave the fiber. It's important to say we do not have rays of light bouncing in the core, and now they're free to go off at whatever angle. It is one beam on axis with the fiber, and the diameter of the beam is just getting larger. And yeah, the way we can model this beam is a Gaussian beam where the beam waist is located at that fiber end face, and that beam waist is equal to the fiber's mode field diameter. Because that mode field diameter is going to be relatively small as Gaussian beams go, that's what we needed to do. We need to make that mode field diameter small so we get single mode light guidance in the wavelength we care about. Because of that, we have a small Gaussian beam waist, and therefore you get a pretty highly divergent beam as Gaussian beams go. So once again, here's putting some math behind that. These are the same equations we saw previously for Gaussian beams, and I've substituted in, instead of beam waist, I've substituted in the mode field diameter divided by 2. Of course, beam waist refers to a radius, mode field diameter is a diameter. So yeah, we can calculate the Rayleigh length, we can calculate the far field divergence, we can calculate the beam radius at any z distance from that fiber tip. So putting some real numbers behind this, let's look at SMF28 fiber. That's a very common telecom fiber in the world used to link continents for telecommunications. And that's the example I'm going to use for this talk, just like in the last talk. So that fiber has a mode field diameter at 1550 nanometers of about 10.4 microns. So if we plug 10.4 microns per mode field diameter and we plug in 1550, we get a Rayleigh length of about 55 microns. So yeah, something like 6 core diameters is all before that beam is already expanded quite a bit. You can see this graph here is just showing us the beam radius versus the distance from the fiber. If we get even 300 microns away from the fiber, we already have a beam that's much larger than what we started with. So you can see it diverges very quickly, and that's because of this small waist. And then, of course, it does diverge linearly in the far field. So we can calculate that angle, 5.44 degrees. And that angle is what we see as that cone of light that the fiber is going to emit. And that is different than what you'd get if you calculated it from the fiber's NA. Okay, so to sum all that up, I have a animation to watch. So here's just talking about the concepts I just went through. So we have a fiber, core in the cladding, single mode fiber. We have a beam propagating in the core. And because we're in that waveguide, that core clad structure, we have a beam that has a constant diameter, and that's the mode field diameter, right up until the fiber end face. Once we get to the end face, the beam starts to expand, as Gaussian beams do. So that beam has a beam waist at the fiber end facet, that's equal to the fiber's mode fill diameter, and then beyond that it expands. First it's kind of in a curve, and then it's going to be linearly in the far field. There's the Rayleigh length, where the beam waist, or the beam diameter, is about factor of square root of 2 larger than the beam waist. Beyond a few Rayleigh lengths is where we're going to be in the far field. So if the distance is much larger than the Rayleigh length, that's where what I would call far field, where we'd have that linear divergence. And then of course we can calculate the beam radius at any distance z away from that fiber end face using the equations in the previous slide. So that's the model, and here is that microscope image again with a little more info. So this is a fiber called SM600. It's single mode in the red visible wavelengths. We have 635 nanometer light propagating in the core, and then we have a mode filled diameter of about 4.5 microns, which means a very highly divergent beam. And this far field divergence angle is about 5.3 degrees. So this distance, the fiber's cladding is 125 microns. So the core is much smaller. So even over here, we're much further out than the Rayleigh length. And so we see linear divergence of that beam. The beam also grows less intense at any given spot. The power density is less because it's spread out. So I've said a few times in this talk, divergence is not a function of NA like it is for multimode fibers, but there are some intricacies here that I think are worth going over. So so what we're saying here is, wait, does NA really have no effect on output angle? So a little rewind to the last talk, we talked about designing single mode fibers, and we talked about index profiles, a step index fiber, you have a cladding with a certain index, you have a core with a certain higher index. That's this kind of Y displacement here. And then the core, of course, also has a diameter. So that's what we see here in the index profile. This is like looking across the fiber. And if we want to have a fiber to be single mode in a certain wavelength range, that we can choose a number of different index differences and core diameters to make that happen. That index difference is what we would express from a fiber designer's point of view as the NA. So that's what we see in this equation here. NA it expresses the difference between the core and the clad index. Now it's really important to note, sometimes in certain manufacturers' fibers, if you look at their spec sheet for a single mode fiber and they give you NA, it refers to this. That's how it would be for the fibers we manufacture and sell here at Thorlabs. But some other fiber companies, including Corning's SMF28 we talked about, they specify an NA, which is basically from like a microscopy point of view. NA is the sign of that angle of divergence or convergence. And so that what they're looking at is this far field divergence angle that we'd see, and then they back calculate what would the NA seem like from that. And sometimes on a spec sheet, they don't say which is which. So got to be careful with that when we're looking at fiber specs. But again, from a fiber designer's point of view, I'm thinking of NA as difference between core and clad index. So over here, standard telecom fiber, we could have a low NA, larger core, and we get a certain cutoff wavelength. This smaller core fiber, we have a much higher NA, much smaller core. We can get the same cutoff wavelength, so the same single mode operating wavelength range, anything larger than the cutoff. And the big difference is a much different mode field diameter. Now, as we just said, I just went over smaller core, larger NA. That's this fiber, means a smaller mode field diameter. That smaller mode field diameter means smaller Gaussian beam waist for that output beam. And that means a larger divergence angle. So if you do the calculations for these fibers, we can get like 5.97 versus 15.84. Obviously, this fiber has a much larger divergence angle, and it is because we have for a certain single mode operating wavelength range, we have larger NA, smaller core. So the NA is kind of, partially affects it, but not directly. And it is worth noting, if we were to plug these NAs into that multimode equation, we would get larger angles than we see here. So yeah, NA does indirectly affect how quickly the light's going to diverge from the fiber. Okay, the last thing to go over for the output of single mode fibers is, well, what do we do with this highly divergent Gaussian beam that comes out of the fiber? What can we do with this? And that's this last section. So talking about how do we work with this beam? So really all it is, like I said, is a Gaussian beam that's highly divergent. So we can do things like focus that light, we can collimate that light, and really all that means is we're going to use lenses to turn that small waist, high divergence Gaussian beam into a beam, let's say, with a very large waist, not very divergent, and a very long Rayleigh length. That means it's going to be roughly collimated. You can never have a beam that's going to be the exact same diameter along its entire length, just due to the nature of Gaussian beams, but you can have it, not expand very much as it propagates, or you can even put the waist, some finite but very far distance away, so that that beam, is roughly the same diameter for a very long propagation length. So we can use things like the thin lens equation when working with Gaussian beams. There's a really good reference here that talks about, there are some additional terms you need to put in the thin lens equations if the focal length of the lens is close to the Rayleigh length of the beams. If the focal length is much larger than the Rayleigh length, which would be the case here for a highly divergent beam out of a fiber, you can basically use the standard thin lens equations. But there are some terms here that for certain circumstances matter. Also, if we're trying to get a roughly collimated beam, we can use an equation like this just to look at the mode field diameter and the focal length of the lens and the wavelength, and approximate the diameter of this roughly collimated beam. But in general, all we're doing here is we're turning a highly divergent Gaussian beam into a Gaussian beam that's not as divergent because we've traded that off for a larger beam waist. Okay, time to move on to the next section. Whoops, I'm on mute. Okay, so time for the next section. We've talked about how the light exits the fiber. So now we're going to talk about the reverse, potentially a more complicated subject. How does the light be coupled into the fiber, into this waveguide? So coupling into single mode fiber, to put it lightly, is not a trivial task. We're trying to get this light into a very small core, a very small waveguide. So we need to meet a lot of parameters to make that happen and get a lot of the light coupled in. Things like good interface quality on the fiber, good quality of that focused beam, and also very fine mechanical positioning of the fiber tip. And we're going to talk about some tips and tricks on how to make that happen in a hands-on way. But first, talk about the model. Really, it is this Gaussian beam theory we're going to use to model coupling, just like we've modeled the output of the fiber. Here's a quick comparison with multimode fibers. Multimode fibers are much easier to couple into. They kind of don't care what anywhere near as much done as picky. We can use the ray optics model. All we're trying to do is focus a spot of light on the fiber end face and not have it that focusing exceed that acceptance angle of the fiber. It's best to fill about 70% of the core and the NA to get really good coupling efficiency. Beams with a variety of optical properties. We don't need that Gaussian intensity profile. You can have a top hat beam, you can have a Gaussian beam, you can have a very small underfilled spot, you can have a spot that fills almost the whole core. All of these things are okay. Plus the core of these fibers is tens of microns at the least. And so mechanical positioning isn't as hard. So that's the multimode case, and once again for multimode fibers only. And we're going to contrast that for single mode fibers. In the single mode fiber model, really again, this is the opposite of output of the fiber. That fiber is looking for light with a certain mode fill diameter and a certain roughly Gaussian intensity profile at that input facet. And all that matters for the light to couple into that fiber waveguide, all that matters is that we present the fiber with the correct spatial intensity profile, the correct diameter, correct profile, perfectly aligned at that fiber end face with the end of the fiber core. So if you're hitting that fiber core with light that has the right spatial intensity profile, it couples in. And if you don't, then it only couples in the fraction of that light that would be that profile, that is that profile. So if you coupled in a top hat beam, you're not going to couple as much light in from the edges of the beam compared to the center. So yeah, putting that into some more formal terms, we need Gaussian intensity profile at that end face. Diameter of that spot must equal the mode fill diameter. We need normal incidence on that fiber's end face, and the beam waist needs to be in plane and centered on the fiber core, no offsets. So just like with the output of the fiber, we don't really care of the NA, quote unquote, of that input beam. Again, this is going to be a Gaussian beam that's being focused down to a beam waist. That incident angle is always 0. It's going to have some certain divergence or convergence depending on the wavelength of that focused light and depending on the spot size that we're trying to achieve. And yeah, does not directly relevant to the fiber's NA. All that the fiber cares about is we present it with the correct intensity profile, perfectly aligned with that fiber core. Yeah, all we have to do. So that makes it sound easy, right? Let's talk about coupling efficiency. How much light can you get into the fiber? So coupling efficiency, really all I'm talking about here is the power of our free space beam compared to the power of that beam coupled into the fiber. And we can express that as a percent. So it turns out it's really hard to get all of our input light, perfect on that fiber end face. So 100% coupling efficiency is pretty hard to do. Really in a lab environment, if we're setting something up, with some lenses and some fibers on a breadboard, if you're getting over 85% coupling efficiency, that's pretty good for a single mode fiber. This table here, we've adapted this from some of our products here at Thorlabs that involve single mode fiber coupling. And these are some benchmarks for some really good coupling numbers. As you can see, it's actually easier at longer wavelengths. If we go to shorter wavelengths, it gets harder. We go from 90% to 75%. And if we were to go further into the visible and UV, it really gets really hard to get good coupling into single mode fibers. That's due to a couple effects. First of all, as the wavelength gets shorter, we're talking about a smaller mode fill diameter, a smaller spot size. That's harder to do. Mechanical positioning of all the components becomes much more critical. And additionally, shorter wavelength light, if you do have anything that's not perfectly focused, it's much more prone to scattering. So it's just harder to work with in general when you're trying to do things with these tolerances. So yeah, it gets harder with shorter wavelengths. And it's also worth noting, if we have a beam that does not have a Gaussian intensity profile, not a Gaussian beam, coupling efficiency is going to be pretty poor, and it's pretty hard to overcome that. We can actually put some numbers behind, not optimal fiber coupling, and there's some equations here. For instance, we can look at if the beam waist and the fiber's mode fill diameter don't quite match. So we can plug in this is the waist of the input beam, and this would be the mode fill diameter of the fiber. That's the example we're showing here. So the cartoon shows a Gaussian beam with a very small beam waist. We've focused the light a lot smaller than it needs to be. We're trying to go into SMF28 fiber looking for a 10.4 micron beam. So the table here, you can see, of course, at 10.4, the theoretical coupling efficiency is 100%. If we go much bigger, up to 16 microns, we see the coupling efficiency suffers, and that makes sense because the spot's a lot bigger than what the fiber can guide. Here's in my opinion, the semi-counterintuitive part. If we couple a beam in that's much smaller, 5 micron beam waist, we also see a drop in coupling efficiency. Now, if this were a multi-mode fiber and you have a large core with a small spot going in, there's no problems there. All the light's going to go in the core and be coupled into the waveguide. The problem is the single mode fiber, it can only guide a mode with that one spatial intensity profile, that Gaussian, roughly Gaussian profile. And because this beam is too small, most of the light, or a lot of the light, doesn't match that intensity profile. And that's why we see, as we get a smaller beam, we see the coupling efficiency suffers, because we're not presenting the fiber with light that it can guide, because it can only guide that one mode. So yeah, that kind of is the deal with if your spot doesn't match your fiber. It is also worth noting, look what happens when we're just a little bit off. If we go to 11 or 9.5, or even down to 8 microns, it's still pretty good. It's when we get radically mismatched spot sizes that we see poor performance. And we also have equations up here for lateral offset and angular offset. So this would be if we don't have that spot perfectly aligned to the fiber tip. So those are some equations where you can calculate things, and here's an example. What we're showing here is a Gaussian beam with the correct beam waist, 10.4 microns, but it's been translated a certain amount off, so it's not centered on the fiber core. So once again, the fiber is not seeing that correct intensity profile at the core. I think this is pretty interesting. Lateral offset, 1 micron, okay, coupling efficiency is still pretty good. Look what happens even when we go to 2 or 3 or 5 microns of offset. That's not very much. That's trying to position this fiber and this lens and this beam so that everything is focused correctly. If we're even 3 microns off, we can only get to 72%, call it, coupling efficiency. So that's what I mean when I say the level of mechanical positioning accuracy that you need to fine-tune that coupling is significant. Things like differential adjusters, which we're showing in this neat diagram, can be very useful. That picture we showed a couple slides back of that translation stage, that's a product here at Thorlabs where those are a flexure stage with differential adjusters. I personally like those a lot for aligning single mode fibers because you can make very small mechanical tweaks. But yeah, it's very hard. If you're off by only a few microns, coupling efficiency really suffers. So yeah, we need very fine ways to fine tune that alignment. We're going to talk about that again in a few slides. So talking about, well, what kind of optics do we need? How do we focus down to the correct spot size for a single mode fiber? Really, that's going to be a function of the wavelength of the light, the fiber's mode field diameter, and the characteristics of the input beam. Like for instance, what's the waist of that beam? What's the Rayleigh length? Once again, we can use these thin lens equations with these Gaussian modifications. Again, I would point you to that same reference. That's very good. We can talk about things like magnifying the input beam waist to the output beam waist so that we can get the right, focused beam waist on the fiber. And then again, just like collimating, there is a simplification we can use that's pretty good. So if we have a Gaussian beam that's, I called it quote unquote collimated. So let's just say, very, very long Rayleigh length, it doesn't change diameter much along its length. As an example, something that could come out of like a Heaney laser. We can kind of treat that as collimated, and we can say, okay, it's got a constant diameter, or at least it has a diameter at the input into that focusing lens. And we can use this equation here to approximate, the spot size it's going to produce, which we said equal to the fiber mode field diameter. If we solve that equation for the focal length of the lens, it's going to be a function of the beam diameter, the fiber's mode field diameter, and the wavelength. And that's a really, really helpful equation for picking a lens to couple a beam into a single mode fiber. That's what we're using in this example here. We're trying to go into SMF28. We have a 3mm collimated beam at 1550. And it turns out you can use a lens with a 15.8mm focal length, and that'll get you that 10.4 micron spot. Now it's unlikely that if you look at the Thorlabs catalog, let's say you're going to get a lens that matches exactly that focal length. So typically the guidance is if you can't get it exact, go with a slightly shorter focal length lens. That's going to give a slightly smaller spot. As we saw on I think it was 2 slides ago, slightly smaller, slightly big spot is okay. It's better to go slightly small so we're not focusing light onto the cladding, can scatter and cause problems. Yeah, so 15.5, let's say, maybe is in the catalog, that'll work really well to couple into this fiber with very high coupling efficiency. So now that you've picked the optic, the next couple slides, we're going to go over a few tips and tricks on how we can actually, make this happen and couple into the fiber. So the typical alignment configuration would be to have the light incident on the fiber tip, and then the other end of the fiber plugged into like a power meter or a photodiode or some way to read the output power, the output light from the fiber. And then we can align things to get the most light coming out of the fiber, which will signify that we have the correct coupling alignment at the fiber tip. It's important to have everything parallel and on axis. So I'm a big fan of having that input beam centered on the lens and having that lens and the fiber tip, orthogonal or aligned to that optical axis. We put the beam in the center of the lens, and then we only need to move the fiber tip in X, Y, and Z linear movements to get that fiber tip lined up with the beam waste that focusing lens is producing. If we start introducing tip and tilt into the fiber, or tipping and tilting all the components, it's too many degrees of freedom, and it's pretty hard to get the optimal coupling efficiency. But if we only move things in X, Y, and Z, already having that beam and the lens aligned and already having the fiber tipped and tilted so it's aligned is the way to go. You can use things like a folding mirror pair between the light source and the lens, and that allows you to not just tip and tilt the beam, but also translate the beam to get it in the center of the lens, and that's a pretty good way to go for aligning. Once you have a setup like this, it can be kind of challenging roughing in the setup so that you have a very small focused spot of light and we have a very small fiber core, and it's hard to get those anywhere near each other so you can see some output on your power meter and start aligning. So we can use some tips and tricks to rough in the setup. The first would be we can substitute that single mode fiber for a multi-mode fiber. Let's say one with like a 50 or 100 micron core. It's a much bigger target, and then we can get some sort of signal, and then we can unplug the multi-mode fiber, plug in the single mode fiber. If the cladding diameters are the same, or if we have connectors, they're going to be in roughly the same spot. You can usually get some sort of signal in your single mode fiber then and start aligning from there. So that can be helpful. And another tip is, of course, these coupling optics, we're here showing a reflective collimator for coupling, but these coupling optics are really a collimator in reverse. So we can actually run visible light backwards through the fiber we're coupling into, and that'll give an alignment beam. So you can see, are things close? You can get that alignment beam and then the input beam coaxial, for instance, and then you can go from there, or collinear. So yeah, products like this handheld fiber coupled laser source can be very helpful for that, where we can get a red alignment beam that corresponds to where the fiber tip is relative to the lens. When we're actually aligning, it is possible to get stuck in what I'd call a local maximum if you're using these XYZ adjustments. And really the reason for that is, like we're showing in this cartoon here, let's say the beam waist is right here and our fiber tip is up here. So if I call Z the direction along the optical axis, I need to move Z to the left. The problem is if I do, it's actually my output power, my coupled in power is going to decrease, and I would need to fix that by adjusting, let's call it Y, to bring myself to my core to the right spot. So you can't just turn X, turn Y, turn Z until you get the highest number and be done. You really need to use an iterative process, and the idea is adjust X and Y for maximum power. So that's trying to center the fiber in this beam. Then, but you're probably not going to be perfect. Then move Z, well, write down the output power, then move Z in one direction, re-optimize X and Y, and see if that power increases over the original. If so, we're going in the correct Z direction, and if not, we're going in the wrong Z direction. You can iterate through this, adjust X and Y, move Z a little bit, readjust X and Y, move Z a little bit, readjust X and Y, and you can step up to the best coupling efficiency. That'll guide you to the beam waist location with this iterative process. That's what I'd recommend. Okay, so the next topic, switching gears a little bit, I'm going to talk briefly on launching high power beams into single mode fibers. Really, the crux of this is single mode fibers need very small spot sizes, focus spots to couple into them. And because of that, even beams that have relatively low total power, you can create a very high power density on that fiber tip. So looking at this table here, let's say we have, a 1 milliwatt or 10 milliwatt or 100 milliwatt beam, not really quote unquote high power. If we focus those into, let's say, a 9 micron spot, we're going to get these power densities. So what do those numbers mean? What I've done in this column is I said, okay, if you have that power density in a 1 millimeter diameter beam, that total beam power would be 150 watts, 1.5 kilowatts, really high power beam. So that is what the fiber tip is kind of seeing in that area of focused, intense light. And we can cause issues with burning the fiber tip because we have, even with a relatively low power beam, we can have a pretty high power density. The ultimate limiting factor here is what can the silica glass the fiber is made out of handle. So there's a lot of different sources, but one I found said, a little under 100 kilowatts per centimeter of beam diameter. And that would tell you for a 10.4 micron mode fill diameter and an SMF28 fiber, you can get in something like 50 watts before you have to worry about the actual silica glass degrading. In practice, though, we very rarely reach that theoretical threshold. There's always something that limits it. There's always the weakest link, something that's going to limit it to a lower power before we get damage at the fiber. Basically, the big problem is any light that's not coupled into the fiber can scatter and cause trouble. So some tips if we want to try to get close to that theoretical power handling of silica glass. We want to use fiber end faces with no AR coatings because AR coatings are going to be a lot lower power density they can handle. Got to make sure that everything is clean and flawless. Any kind of dust or dirt can scatter light and cause problems. Here we really want to make sure that the beam waste of that coupled beam is as close to perfect as possible of a match to the fiber's mode fill diameter, so we don't have a light that's not coupled in. When we're doing that alignment procedure, we want to have the beam power turned down as low as is practical. So when you're aligning, you're going to be walking that spots around the fiber, trying to get it on that fiber tip. So you don't want to be doing that with high power light and focusing on the cladding and things like that. So yeah, align and then increase the power. And even still, we do want to inspect the end faces frequently for damage. Here's what we're showing here is a damaged end face. Maybe there was a speck of dust or something, caused the light to be absorbed and scattered and burn the fiber tip. So we do want to inspect for this sort of thing. We can do things like look at the fiber end face under a microscope, but we can also do things like look if the fiber's output pattern is Gaussian, because if not, that could imply there's something up with the fiber tip. And like everything with single mode fibers, it's harder to do when you have shorter wavelengths of light. We got smaller spot sizes, higher power densities. We need better mechanical positioning. And that shorter wavelength of light is more prone to scattering. So there's a couple of different reasons that makes it even harder at short wavelengths. All right, switching gears once more. We've talked now for a while about coupling into single mode fibers, Gaussian beams with good beam quality. But that's not really what you always come up against with single mode fibers. And I thought it was interesting to talk about kind of the opposite case. What if we have a very non-Gaussian messy beam and we're trying to get some of that light into the single mode fiber? What it comes down to with call it incoherent light, you don't have very much intensity in each spatial mode. And of course, that fiber can only accept one. So we can't really couple in very much power. We're going to, by definition, have very low coupling efficiency. But we can get some light in. There is going to be some light in that spatial mode the fiber is looking for. And we actually can couple in enough light that for certain applications, it's sufficient. Things like broadband spectroscopy, you can couple white light into a single mode fiber. We can do some really interesting science with that. So that's really what we're looking at here. My example is, what if we have a tungsten filament, a glow bar, or incandescent light bulb, and we're going to try to couple in as much of that white light into the single mode fiber. How do we calculate that maximum light coupled in? To do that, we have to look at this equation here, which tells us the spectral power density for each one of those LP modes, out of a black body emitter, which is basically what that filament is. Of course, the single mode fiber can only accept that fundamental mode. And if we run through this equation, most of these things are constants. We do have the filament temperature of that tungsten filament. For a 2700K filament, we can get about 0.46 nanowatts per nanometer. So not very much. That fiber's fundamental mode, if you recall, we said this once or twice in the first talk, it's actually 2 linear polarization modes, orthogonal modes. We treat them as one. So we can double that number. We get about 0.92 nanowatts per nanometer. And that's really about the maximum into a single mode fiber with that filament temperature. This is assuming the fiber is basically touching the filament. So we'd call that butt coupling, which isn't practical with a hot filament. So any kind of coupling optics are going to decrease this number. The best we can really do is a 1-to-1 imaging of that filament onto the fiber core. If we try some tricks, it turns out none of them really work. You might say, what about using a higher power light bulb, 150 watt instead of 100? The way that's accomplished is a thicker filament, and we're still just imaging the filament onto the fiber, so we're not going to get any more power. Additionally, if we what if we say, hey, magnify the filament or demagnify the filament onto the fiber tip? Turns out we don't get more in because it's still only that one spatial mode. So yeah, we really can't get around this. We can increase the filament temperature, and that's really the only thing. But yeah, I think it's an interesting thing to think about. Imaging that filament onto a portion of it onto the fiber core, we're going to get a certain optical power per wavelength interval. Not very much, but enough to do some things with. Now you might ask, what happens to the light that doesn't get coupled in, but is incident on that fiber's end face? So this is something that comes up in a lot of different applications. What happens to the rest of the light that's not coupled into that fundamental mode in the core? And that's what we're showing with this image here. Here what we did is we have a few meters of single mode fiber. It's single mode in the visible region. And we've hooked it up to a white light supercontinuum source. And you can see at the end of the fiber, this white light at the tip, that's light that is coupled into that fundamental LP01 mode and propagated through the whole length of the fiber. This yellow light is light that is not coupled into the core, and it is not able to be guided through that fiber's waveguide very well. That being said, as you can see, it does propagate some length as it's gradually scattered and lost. We would call these cladding modes, higher order modes, in general, just weakly guided, other modes besides that fundamental mode. And yeah, they can make it through short lengths of fiber, and that can cause trouble for some applications if you're only using a short length of fiber, let's say. So these can be something that we need to watch out for, especially when doing things like coupling in not a perfect beam into the fiber. Luckily, we can detect these and we can get rid of them. So to detect cladding modes or coating modes, any kind of loosely guided mode that's not supposed to be there, the biggest thing we could take advantage of is they are loosely guided. So they're going to be much more sensitive to bending the fiber compared to the fundamental mode. So we can do things like, if we bend the fiber, do we see any light leak out? That's kind of what we're seeing in this example here. We can look at the output pattern of the fiber, and if we bend the fiber, if you recall in the last webinar, we had a little video of bending a single mode fiber, and we can see the output pattern doesn't change because that fundamental mode is not sensitive to bending. Well, these other modes are, and so if we bend the fiber, we can remove these modes, or they're going to fall out, so we can see that fiber's output pattern changes. And yeah, we do just that to remove the cladding modes. That's the example we're showing here. We'd call this a mandrel wrap, which is basically just bending the fiber around something. And as you can see, the input is here. We have no light scattering out of the fiber because it's all coupled in. As soon as we bend the fiber, we can see this blue light. What that is, it's not a cladding mode. It's a higher order mode below the cutoff wavelength, but it's the same effect. As soon as we start bending the fiber, we see that mode leaking out throughout the fiber, and then as the fiber stops being bent, it's no longer leaking. So this is a great way to filter out any of those higher order modes if they're in the fiber. There are other methods as well, things like, general term would be mode strippers, things like index matching gel that can destroy any kind of total internal reflection happening at that coding to air interface and get rid of those modes. Okay, so that's all we have on fiber coupling. That was a long section. Rest assured, the next one will be much shorter. Just going to speak briefly on fiber to fiber connections at the end of the talk. So the idea here is we've talked about using lenses and things to deal with free space beams and fibers, but we actually can transfer the beam from one fiber to another without going to free space. We can do things like fusion splices, which you see here, melt the fibers together. We can do things like have the fiber terminated in a connector and use a mating sleeve to connect two connectors together. And many of the same concepts apply from that, the input and output of fibers. Really all it comes down to is the fiber that's receiving the beam from the first fiber. Again, all it cares about is getting light in that correct spatial mode presented to it at that fiber core. If we do that, we'll have good coupling efficiency, and if we don't do that, we're going to see some loss. So yeah, like I said, the second fiber has to receive a beam that matches the spatial intensity profile of the mode it can guide. So if you're talking about coupling two fibers together, what that means is the mode field diameters of these two single mode fibers must match. So if we have two fibers with identical mode field diameters and we have perfect mechanical alignment, you can get basically no loss through a splice or a junction. If we do have some mismatches, mode field diameter, let's say, we can calculate it using these equations. These are basically the same equations we were looking at for a free space beam into a fiber. Now we're just, instead of saying beam waist of of the beam and the mode field diameter, it's just the mode field diameter of the first fiber versus the second fiber. We can see a mode field diameter mismatch in addition to these mechanical offsets of these beams. So some examples. This first one I think is pretty interesting. Let's say we have two fibers, these two example fibers we've been using, and they have a different mode field diameter, 3.57 versus 10.4. If we have light in the first fiber and we're going to transmit it from the small core to the large core, if this was multimode fiber, you'd get basically 100% coupling. If it was, a 50 micron core to a 62.5 micron core, the coupling is going to be very good. And if you go, right to left, you'd expect it to be bad because with large core to small core. Well, it turns out for these single mode fibers, this is actually bidirectional. So we're going to get a loss. We're only going to get about 38% transmission, no matter which direction we go here, even the smaller to the bigger. The reason for that is, again, we're just not presenting the receiving fiber with the mode that it's looking for. So it can only guide some fraction of that mode. So yeah, same loss regardless of the direction when we have a mismatched mode field diameter. And similarly to what we showed with the spot sizes from your lens, if it's pretty close, 10.4 and let's say 9.5, you're going to get very good coupling efficiency. It's when we see these large differences that we see a lot of loss. And then last example, mechanical offset. Once again, similar to coupling in, if you have any kind of offset, you see the transmission or the coupling efficiency falls apart pretty quickly. So that's, again, very similar, same equation. So it behaves exactly the same as coupling in a free space beam. Okay, so that's everything. So I want to thank everyone for listening. This is single mode part 1 and part 2 have been pretty fun to talk about for me. I hope you all enjoyed. And if there's time, we can take a few questions.
Hi, Dave. Thanks for giving your presentation as always. We do have a few questions, and I'll rattle them off now.
Sounds good.
Okay, first one just came in. So do the lens equations for matching the MFD for coupling still apply if using a doublet lens instead of a singlet?
Yeah, so they still apply in the sense of, we're trying to get a Gaussian beam waist that matches the fiber's mode field diameter. A doublet lens is going to have a certain effective focal length. And so if I back up to that slide, yeah, you can still use this equation. You're going to have a certain effective focal length of that doublet lens. You're going to have a certain input beam size. shooting for a certain fiber mode field diameter. So yeah, you can still, same logic, whether it's a spherical singlet, which isn't going to give you a very good spot, an A-sphere or a doublet or anything like that.
Yeah, and I guess a lot of people use microscope objectives, which are, multiple lenses. So.
Yeah, exactly. But yeah, still going to do the same thing. Great point.
Okay. So why is it so hard to tune the beam waist to exactly the mode size you want experimentally?
Well, I think what it comes down to is, again, single mode fibers, the whole way we make them single mode is we make the core very small, and that way only that one spatial mode, quote unquote, fits in the fiber. So the mode field diameter is just very small relative to the wavelength of light. I think in the last talk we talked about, the core diameter of the fiber is only a few wavelengths wide. The mode field diameter, same thing. For SMF28, 10.4 micron mode field diameter, 15 nanometer light. So it's, these are pretty close. This is 1.5 microns, this is 10.4. So when we're trying to focus light down that small, everything matters. It's just any kind of, mechanical positioning error, any kind of aberrations, like if we were using a spherical singlet lens, all of that, matters. And so it's hard to get that beam focused to the correct spot size without any kind of aberrations. We need to make the right core size, but also not mess up the Gaussian intensity profile of the beam. So if the beam is focused elliptical, let's say, then you're not going to have the right spatial intensity profile, and you're not going to get good coupling efficiency. So yeah, it's just because we're working with very small waist, highly divergent Gaussian beams, it makes everything a lot harder experimentally in real life.
Yep. So, okay, next question is about the NA. So, you talked a little bit about how the NA is, not completely intuitive in a single mode fiber situation, but, a higher NA still means a larger divergence angle. Is that correct?
Yeah, absolutely. I would add to that a higher NA and at the same single mode operating wavelength range. So same cutoff wavelength, same bend edge. A higher NA is going to mean a fiber with more divergence, and that's all because if you're using a higher NA, in other words, a higher index difference between the core and the cladding, then the fiber designers have had to make the fiber core small to maintain the same cutoff wavelength. If we just went to a higher NA, let's say we took this blue profile, we just made the core index a lot higher. So it's got a big core and a higher NA. That's going to mean the fiber is going to be single mode somewhere out in the mid IR. The wavelength increases where it's single mode. So the fiber designers have had to make the core smaller when they've made the index difference bigger in order to get that the same single mode operating wavelength range. If you look at single mode fibers on the market, you'll see things like bend insensitive or flex fiber or things like that. That usually means high NA, small core. And because now the core is small, the mode field diameter is going to be relatively small. And the mode field diameter being relatively small means we get more divergence from that output beam. That's how we see this fiber has far field divergence much more than this fiber is because the core is smaller, the mode field diameter is smaller. The fiber designers have had to do that because we have this higher index difference. The point I was trying to make though is this NA, you can't plug this into that. NA equals N times the sine of the output angle. You won't get this number because the divergence occurs by a different mechanism.
Yeah, from what I remember, everything's kind of buried in equations, right? Like with the V parameter, which I think you talked about a little bit last time. It's very indirect. Okay, so would the bending of the optical fiber during setting a system up decrease the coupling efficiency?
Yeah, so that's something that I think we covered some in part one of this webinar. Single mode fiber, one of its virtues is that fundamental mode is it's very bend insensitive. So it doesn't really care if the waveguide is bent or if it's straight. There are some limits to that if you really bend the fiber a lot, or there are some subtle effects, but by and large, that fundamental mode propagates through the fiber, and it's not influenced by bending the fiber. So because of that, when you're aligning this setup, if you're only putting in one mode into the fiber and you have like the right spot size, you can bend the fiber, and you shouldn't see a difference out the other end of the fiber as far as the transmitted optical power. So in theory, we're not really going to see differences in the coupling efficiency based on if the fiber is bent or straight. That being said, by the nature of doing this alignment, you're going to be moving the fiber, so that beam is going to be incident on different parts of the fiber, and that's a really great time to couple light into the cladding and get higher order modes, and those are bend sensitive. So you have a short length of fiber and the alignment isn't perfect, you might be putting some light into the cladding or the coating, which could propagate through, and if you bend the fiber, you're going to kick those modes out of the fiber. You might see a different power level. So it is best practice for like a lab setup, let's say using single mode fiber. Most people like to tape down the fiber so it doesn't move from day to day or experiment to experiment. That's a best practice sort of thing in case you have cladding modes, or in case there is sort of like, for instance, if you bend the fiber, you can get like polarization effects, which we want to avoid. So best practice is, shouldn't really be like, if the fiber is going to be used bent, keep it that way. If it's going to be used straight, keep it that way. Theoretically, though, that fundamental mode of the fiber is relatively bend insensitive. I know that's a long answer, but hopefully it's helpful.
Yeah, thanks. Quick question. So do all of these equations apply to PM single mode fibers as well?
That's a good question. I don't want to say 100% yes, because it's not something that I've specifically looked into in preparing for this talk. But I can say that in general, the operating principle of a PM fiber, it's a single mode fiber, right? So a small core only guides one mode. Can we get back to like these equations? It's a single mode fiber, it only guides one mode, and then you have stress rods on either side of the core that create some stress induced birefringence in that core. So it's going to treat those linear polarization modes differently, and things like bending the fiber now, it's not going to scramble those polarization states like you will in a regular single mode fiber. So there may be some differences in like, you have to pay attention to the slow axis and the fast axis, and you might have things, behave a little bit differently. Usually when you have those stress rods in the fiber, the core ends up being elliptical as well because they kind of squish the core. So you're probably going to have a different mode field diameter at the slow and the fast axis, slightly different. And you have to look at like those two orthogonal polarization states separately versus kind of what we're talking about here. Everything is averaged together. So that's some of the differences there.
Okay, one last question. I think this came in when we were talking before. So what's the main difference if you use a single lens versus a microscope objective for coupling?
Sure. So again, all the fiber cares about is that it gets its correct spot size and correct intensity profile of that spot. That's all the fiber cares about. So from the fiber's point of view, it kind of doesn't care. The big difference has to just do with how optics work. So if you use a spherical singlet, you're going to get spherical aberrations. Yeah, even with a single wavelength of light. So you're not going to have that. You're going to take that Gaussian beam and transform it into a not perfectly focused spot. Things like an aspheric lens can work really well for a single wavelength of light because they get rid of that spherical aberrations. And so you can get much closer to, people would call it like the diffraction limited spot. That means you're basically purposely focusing that light, and you can maintain that Gaussian intensity profile right down to that small spot. Microscope objectives get used because they're just really, really, really good optics. They're usually, as Pat alluded to, multiple element lenses. So, many different lenses inside of there, optical elements. And so the designers have gone through great pains to cancel out all of the different focusing aberrations the lenses can have. Even things like chromatic aberration, which is not going to matter if you're only focusing one wavelength of light. And so you can cancel out all those different aberrations. You're going to get really a very, very nicely focused beam. The trade-off being microscope lenses are typically only made to work with visible light. Things like the AR coatings on the lenses might not work in the IR. Maybe even the optical, the lens design, I'm not sure. So if you're thinking about like a telecom fiber operating in the near IR, yeah, you would see microscope objectives used less, and things like aspheric lenses or maybe a multi-element lens that's custom designed for the application. That's going to be pretty common. But again, it's all about like better optics are going to get you closer to that diffraction limited spot, which is going to get you to that correct focused spot on the fiber end face and get good coupling efficiency.
Okay, I think that's all we have time for.
That's good.
So yeah, we're going to close this one out. Thanks to everyone who logged on and registered for this event. Our next talk is on November 24th, and that's on acquiring the perfect OCT image. Registration for future webinars can be found at thorlabs.com/webinars, and you can find all of the recordings for webinars like this one there as well. Okay, thanks everyone.